From physics, you learn the different forms of energy. This makes it possible for interacting objects to release or absorb kinetic energy. You are most likely also familiar with electrical energy. This energy is characterized by charging properties which distinguish objects from each other. Heat is another form of energy. In this picture, the red sphere is hot and is thus full of heat energy. The blue sphere, on the other hand, is cold. It lacks heat energy. The hot sphere is now transferring heat energy to the small, colder sphere, which warms up. The small sphere is now passing energy to the cold sphere. You have just transferred heat energy from one sphere to another. Heat energy always flows from hot to cold. However, cold is not a form of energy. It is a sensation that is triggered by a lack of heat energy. With this test setup, you can learn about some of the remarkable properties of gases. As with a conventional air pump, it has a piston, cylinder, and valve. Did you notice that when it comes to gases, volume, pressure, and temperature are directly dependent on each other? As the temperature drops, so do the volume and pressure. However, if the volume is reduced, the gas is compressed, causing the temperature and pressure to rise. However, if a gas is liquefied, or conversely, a liquid evaporates, the temperature and volume behave in a completely different manner. This test setup lets you study this behavior. Now you have heated the liquid up to boiling temperature. However, the sphere continues to release energy. Note the constant temperature indicator as the liquid evaporates completely. The temperature is just now beginning to rise again. As it rises, the volume of the gas increases slightly. A large amount of heat energy has been used to evaporate the liquid. This is therefore known as latent heat of evaporation. Now, take a look at what happens when the energy is removed again. The hot gas begins to cool down. Now liquefaction begins. The vapor releases a large amount of heat energy to the sphere. This is known as latent heat of condensation. However, note the temperature in the cylinder. It remains constant. The gas is liquefied, and the temperature continues to drop. The substance has returned to its initial state. You can now try the experiment again. Incidentally, liquefaction is also known as condensation. The dissipation or absorption of latent heat of evaporation and condensation can also be caused by a change in pressure. The cylinder contains a substance with a very low boiling point that is a gas at room temperature. The gas is compressed, causing it to become very hot. But something else is happening too. The boiling point is shifting upward. Due to the difference in temperature in the surrounding area, which is the sphere in this case, the gas is now releasing heat and will soon start to condense. The temperature remains constant at boiling point until the latent heat of condensation dissipates. Only at that point is the gas completely liquefied. It can then continue to cool down. Now start the procedure in reverse. The grey sphere once again represents the temperature in the environment. The reduction in pressure causes the liquid to cool down, while causing the boiling point to drop at the same time. Since the environment is warmer, as indicated by the grey sphere, the heat now flows into the cylinder. The liquid evaporates. The sphere becomes cold since it is supplying the latent heat of evaporation. Now take another look at the results. Through mechanical motion, you have just heated up one sphere while cooling the other. In practice, however, no spheres are heated or cooled. The aim is to cool the passenger compartment. Now use a suitable method for combining the changes in state in order to transfer heat. By allowing the refrigerant to evaporate in the cylinder, the refrigerant absorbs the heat from the environment. You can start the process over again. The region of heat loss is purposefully located outside. The region to be cooled is inside the passenger compartment. In practice, it would take a lot of work to move individual containers. Instead, the refrigerant circulates in a continuous closed circuit. The refrigerant compressor, abbreviated as compressor, is the driving force in the refrigerant circuit. It draws in the gaseous refrigerant, compresses it, and then passes it on. The job of the condenser is to ensure that the refrigerant dissipates the heat. By doing this, it brings about liquefaction and cooling of the refrigerant. The expansion valve provides the necessary reduction in pressure so that the liquid refrigerant can subsequently expand. The refrigerant in the evaporator reverts back to its gaseous state. The required latent heat of evaporation is provided by the surrounding air, which then cools the passenger compartment. The circuit is thus closed. In practice, an additional component is required. The fluid reservoir stores and provides the refrigerant. More information on the components is available in the subsequent chapters. The boiling point of a substance is the temperature at which it changes from a liquid to a gas, and vice versa. Therefore, the substance evaporates when heat is applied or condenses when heat is removed. From the preceding pages, however, you have already learned that this temperature depends greatly on the amount of pressure applied. If the pressure is reduced, the boiling point drops, heat is absorbed, and the refrigerant evaporates, even at temperatures below zero. On the other hand, the boiling point increases as the pressure increases. The refrigerant gives off heat and condenses, even though it is hot. The relationship between pressure and boiling point temperature is a specific property of matter and is important when selecting the refrigerant for vehicle climate control. Even in a 50 degrees Celsius desert, the condenser should still give off heat to the surrounding air in order to liquefy the refrigerant. The boiling temperature must therefore be much higher. On the other hand, the evaporator must also operate at low outside temperatures, such as for the reheat function, in order to make the refrigerant evaporate. The boiling point must therefore be quite low. Vehicle refrigeration systems usually operate within a pressure range between 2 and 26 bar. This key data can be used to select the refrigerant. The boiling point curve of R134A is a perfect match. Due to its low boiling point, the refrigerant already starts to evaporate at room temperature. For safety reasons, refrigerants must not be highly flammable. The refrigerant must not be an explosive substance. The refrigerant must not harm humans or the environment. Even though it has few hazardous characteristics, it is imperative to avoid contact with the skin and eyes. The refrigerant can cause severe frostbite injuries. In addition, refrigerants can dry out the skin, thus affecting personal health. Refrigerants also must not have any toxic properties. However, the vapors should never be inhaled. Due to their hygroscopic characteristics, refrigerants attract moisture, which is not desired in the refrigerant circuit. Regulations related to handling refrigerants may vary. Please become familiar with country-specific legislation, if necessary. For environmental reasons, R134A will be replaced in the long term. The refrigerant compressor, abbreviated as compressor, keeps the refrigerant circuit moving. It comes in different designs. The reciprocating piston compressor is used in buses. The helical compressor is used when the air conditioning system must run separately from the engine. The vane-type adjuster is valued for its quiet operation and insensitivity to speed variations. Quite frequently, however, the swash plate compressor is used. A magnetic clutch assists in transferring power from the vehicle engine to the compressor drive shaft. This clutch makes it possible to switch the compressor on or off. The swash plate moves the pistons. The pistons generate the necessary pressure and transport the refrigerant. In this example, only 2 pistons are shown, but in reality, several pistons are arranged in a circle around the swash plate. The required valves are fitted in the valve plate. There are regulated and non-regulated swash plate compressors. Variable compressors are used to adjust the rate of delivery to the influencing factors such as engine speed, outside temperature, or desired interior temperature. For this, a mechanically or electronically controlled control valve is used. Using a regulated swash plate compressor, the angle of the swash plate and thus that of the piston stroke is adjusted. The mechanical method of regulation is a simple one. The control valve responds to the low pressure and controls the pressure in the crankcase chamber. If, for instance, the engine speed increases, the compressor draws in more refrigerant and the low pressure drops. The force of the spring opens the control valve. Refrigerant flows under high pressure into the crankcase chamber via the interconnecting channel. The pressure in the crankcase chamber rises. The higher pressure affects the piston crown and changes the swash plate position. The swept volume is reduced, causing less refrigerant to be delivered. The low pressure rises again. A restrictor ensures that the pressure can escape from the crankcase chamber. The compressor thus remains adjustable. As the engine speed decreases, the process takes place in reverse. The control range of the mechanically controlled compressor is 5 to 100%. Change the engine speed by moving the control to the right. Notice what happens. The control valve opens and the pressure in the crankcase chamber rises. The control valve closes and the pressure in the crankcase chamber drops, since the refrigerant escapes via the restrictor. Did you notice that the low pressure is essential for regulation? Electrically controlled compressors are more advanced. The control valve in this case is not actuated by low pressure, but rather by a control unit. The control range is 2 to 100%. Since the compressor can be controlled to practically zero delivery, it is possible to eliminate the use of the magnetic clutch. It is permanently integrated in the belt drive system. There is an absorber integrated in the belt pulley that acts as a belt guard and safety mechanism against blockage. The helical compressor is used, for instance, in vehicles in which the engine does not run when stationary, so it is used in conjunction with the automatic engine start-stop function or electric drive system. This compressor has its own control unit with integrated power electronics. Propulsion is handled by its own electric motor. Inside the compressor are two helices. One is stationary, while the other completes a circular motion. Through motion, a space of varying size is formed between the circling and stationary helices. Refrigerant is drawn in at the outer edge, conveyed inward and compressed. And then reaches the center of the helix. From there, it is compressed into the high-pressure section of the refrigerant circuit. Constantly drawing the refrigerant in and out results in a continuously subsiding process. In principle, the condenser consists of a pipe with multiple bends. Fins which are permanently attached to the pipe increase the surface area, thus improving the exchange of heat with the surrounding environment. The hot refrigerant gas flowing from the compressor heats up the condenser. The outside air flows around the condenser fins and absorbs the heat. The heat exchange works best when the flow of air in the condenser is cool and fast. The effectiveness, when the vehicle is stationary, for instance, is further improved by using a booster fan. Inside the condenser, the refrigerant gas loses heat and then condenses. It leaves the condenser and flows to the fluid reservoir. The condenser is thus dimensioned so that it liquefies the refrigerant safely even at higher outside temperatures. In principle, the setup is similar for all fluid reservoirs. Essentially, it is a compression-resistant container. The opening is connected to the condenser via a supply line. A hygroscopic filter medium is embedded in the lower section. An ascending pipe leads to a second connection. This is where a line connects the reservoir to the expansion valve. The refrigerant from the condenser enters the fluid reservoir. It is buffered in the refrigerant receiver. The fluid flows through the desiccating filter layer. Undesired particles, such as abraded matter, are retained to prevent damage in the refrigerant circuit. In addition, the filter medium is capable of chemically absorbing moisture. The dried and filtered refrigerant is directed upward in the ascending pipe and leaves the reservoir heading toward the expansion valve. The expansion valve provides the necessary sharp drop in pressure in the refrigerant circuit. The valve has a high-pressure connection for the line from the fluid reservoir. A low-pressure outlet leads to the evaporator. The actual expansion valve is basically a restrictor. The thermostatic expansion valve also regulates the flow of refrigerant to the evaporator. In this case, the evaporator return flow is directed through the upper region of the valve to the compressor. At the top end of the valve is a chamber containing refrigerant that is separated from the refrigerant circuit by a membrane. A valve tappet connects the membrane to the restrictor valve. On the other side, a control spring places pressure on the restrictor valve. Control of the expansion valve ensures that the refrigerant is completely evaporated in the evaporator. If the temperature of the refrigerant vapor drops at the evaporator outlet, this is a sign that an insufficient amount of heat was absorbed. There is a risk that the refrigerant did not evaporate completely and that it will enter the compressor as a liquid. This would damage the compressor. The lower temperature, however, is also transferred to the closed refrigerant chamber in the valve head. This causes the pressure in the chamber to drop and the membrane arches inward. The tappet lifts up and the control spring is able to close the restrictor slightly more. Less refrigerant flows into the evaporator. The amount of refrigerant available is restricted until the temperature at the evaporator outlet rises again, ensuring that the refrigerant is in its gaseous state. With the increase in temperature, the pressure in the chamber also rises. And the tappet opens the restrictor again slightly. Evaporation of the flowing refrigerant depends on several factors, such as the temperature in the environment. The amount of heat energy absorbed per unit of time is the ultimate factor. This is called the evaporator output. The evaporator is similar in design to the condenser. It also mainly consists of a pipe. Fins which are permanently affixed to it increase the surface area. The cold refrigerant flowing from the expansion valve cools the evaporator rapidly. The air to be cooled flows around the evaporator fins and gives off heat. A high airflow rate is required for the heat exchange. This is achieved by the vehicle air conditioning fan. Inside the evaporator, the refrigerant absorbs the heat and evaporates. Outside, however, something else is taking place. The moisture in the surrounding air condenses onto the evaporator. The resulting amount of liquid must be diverted. In addition to the components you are already familiar with, there are safeguards built into the refrigerant circuit that protect the system from being destroyed. A temperature sensor at the evaporator outlet functions as a type of anti-icing protection. The sensor indicates if the refrigerant temperature drops too rapidly, which can occur, for instance, if the evaporator output is low due to extreme contamination. To ensure that no liquid refrigerant enters the compressor, it is switched off. There is a pressure sensor on the fluid reservoir. This sensor indicates if the pressure drops too low. In this case, the compressor is switched off. This can occur, for instance, if there is a loss of refrigerant. Likewise, the circuit is shut down if the sensor indicates the pressure is too high. If the high-pressure shutoff fails, then a mechanical safety lock takes over if the excess pressure is significant. The refrigerant then escapes. Refrigeration oils are essential for lubricating the compressor. They ensure that the compressor runs smoothly, since refrigerant alone does not have any lubricating properties. In practice, different refrigeration oils are used. In the past, mineral oil was used in conjunction with the refrigerant R12. As with R12, it is currently no longer permitted for use in the refrigerant circuit. Refrigeration oils must not be intermixed. Ester and PAG oils are also incompatible in small quantities. Sealing compounds and refrigeration oils must also be compatible with one another. A common property of refrigerant oils is their ability to dissolve well in refrigerants. They must not pose a risk to health or to the environment. These substances must not pose a risk of fire or explosion.